Welcome to Optical Communication course. Today we will learn that a fiber refractive index profile measurement. So in last lecture we have seen a measurement of numerical aperture, measurement of a attenuation, that is a loss that we have seen. Now we will continue the discussion regarding the refractive index profile of the optical fiber. Now if you see the refractive index of a optical fiber, so that is important while calculating the numerical aperture of a fiber, or how many number of modes propagating through the fiber that are depending upon that a core of a optical fiber. So that's why a fiber refractive index profile, that is more important to understand that what will be the number of modes propagating through the fiber, and what will be the nature of light that propagating through the fiber. So we'll see here a method of measurement of a refractive index. So that method is called as a interferometric method. And in this interferometric method, if you see that a small fiber sample is used, and that fiber sample is used to determine the what will be the refractive index profile of the optical fiber. Now this sample of a fiber is created by taking a thin slice of a fiber, and that end of that fibers are accurately polished to obtain the square of that particular sample there. Okay, that slice of a fiber here, so that end of that particular fiber are polished in such a way that we'll get that a thin slab of a fiber and a square shape of that particular fiber. And the surface of that particular fiber is totally flat, and it is to be smooth here. And this particular slab is used to propagate the light through that particular slab. And then if we have a microscope, and that microscope will measure the incoming light or outgoing light from this given particular sample of a fiber slice. This is a sample is nothing but a fiber slice, and here we have the microscope. That microscope is called as a interference microscope, or we can say that this method of measurement is called as a enterophoric method of a measurement of a refractive index. So now in this method we can use a two technique or a two different method. Either we transmit a light, or we can reflect the light through the interferometer. Now in the both the cases, if you consider that, so we have that microscope, and that microscope is here, it is to be placed, and that microscope travels normal to the prepared fiber slice faces, or we can say that parallel to the a fiber axis. So means we can see that a light will travel through this particular a sample or a fiber slice, and that can be seen on this a microscope here. So that what happened, whatever the differences in that refractive index due to the different optical path length, so we can see that a fringe pattern. So that is about the interference fringe pattern obtained with an interference microscope from the gradient index fiber. So here the title is about a fiber refractive index profile measurement. So if you consider that a step index fiber, there is abrupt change in the refractive index profile. But if you consider that a gradient index fiber, that profile varies according to the core radius of a fiber there, which is radial distance. So that's why we will use a gradient index fiber to measure the index profile, and that index profile is again depending upon that index profile of a fiber will tell you what are the number of modes propagating through the fiber or propagating within the fiber there. So that's why here we have the a light is propagating through this, and here we can compare that a phase of that incident light with the phase of that emerging light here, because we have the mirror here, and because of that a field of a parallel interference fringe is observed, and that this one is about a interference fringe pattern, and you can see that there is a variation in this refractive index profile of the wave fiber there, and there is a small variation in that fringe, or we can say that we have the a fringe displacement for those particular points within the fiber core, or we can say that we have this a fiber here, and that varies wherever we have that fringes or variation in that particular refractive index in a fiber core, that can be seen here. I can see that this one is a core of a optical fiber, and inside the core of a optical fiber, these are the various points on the, or you can say that a fringe pattern for this core, and outside this one is about the fringe pattern of this a cladding here. So now variation in that fringe can be measured, or or shift in that particular fringe can be measured in terms of a q there, and that variation is nothing but the what will be the displacement occur in that particular fringes here. So we can calculate that displacement a fringe shift that is about a q, and we will obtain that refract difference in the refractive index delta n, and that delta n is equal to what, q into lambda divided by x. That q is about your fringe shift, lambda is nothing but the what will be the incident optical wavelength, and x is the thickness of the fiber slab. So delta n is equal to q lambda by x here. So we'll get that a difference in the refractive index, and we can find out that difference in that refractive index profile using that interference pattern. You can see that here the figure shows the refractive index profile obtained from this fringe pattern, and that is indicated here with a 4 now. Now this is about the radius. Radius is increases, and this is about the index of a profile. Here you can say that a dot that alpha is equal to 2.0. If it is a refractive index profile, alpha is equal to 2.4. Triangle likewise. So you can see that a variation in the refractive index profile of the given particular fiber. Now the limitation of this method is what? We need to prepare the fiber sample or this particular fiber slice very accurately or thin, and through that a light is to be propagating, and then we can measure that interference fringe pattern. So now in this particular method a light beam is perpendicular to this particular slab, and then we will get that interference fringe pattern. But this method is difficult because we need to prepare the fiber sample for measuring the refractive index profile. But another method for measuring the refractive index profile of a fiber is nothing but the measuring that using the induced grating autocorrelation autocorrelation technique. Now in this measurement, we will see that what will be the refractive index profile of your core of a fiber, and how to measure that. Measured is depending upon that creating the delay in the fiber optical signal or a optical light. So now that that delay is created using the beam splitter. Now you can see that here a source, we have the optical fiber, then one mirror is there, and here we use the beam splitter, and in using that particular beam splitter, that two beams are splitting. One beam is propagating through this way here, that is about the original signal, and another here it is delay is created, so another beam is propagating through this, so that's why the delay signal. And at the end, here we have the photorefractive crystal, and that at a photorefractive crystal two signals will reach. One is the original signal and another is about the delayed signal. Now if you see that here we can measure the what will be the refractive index of this particular optical fiber using the autocorrelation function, or we can say that induced grating autocorrelation function. Now two signals are here combined at this particular point where we have this photorefractive crystal is placed, and then if you see that, and that particular signal is reached to this a photo detector. Now because of that particular delay here, because of that original signal and delay, so you can see that there will be a small diffraction, and that diffraction is used here to implement that induced grating autocorrelation technique. And that photo refraction here, so that is nothing but what a phenomena of whatever the signal is propagating through it, and that will give us the what will be the local index of a refraction. And then we will see that there will be the variation in that light intensity from the original signal and the a delayed signal there. Now you can see that here, if you see that there is a variation because of a photoelectric effect when that two lights are superimposed on this photorefractive crystal, and then it will create that interference pattern, and that interference patterns has a variation in the intensity, and that variation in the intensity is nothing but the high and low variation in the intensity. You can see that this is about the intensity variation, that is about a high and low intensity variation. And here if you see that, we can see that there are the variation in the intensity as well as the charge carriers, that is nothing but the electrons and holes, and that's why there is a variation in the charge carrier density, and that's why we can see that it charge carrier distributions according to the variation in the intensity. Now because of that variation in the intensity and a carrier charge distribution at at that particular material or photo, we can say that at this photorefractive crystal, you can see that there will be a charge distributions at that particular place due to the space charge field, and that will modify the what will be the refractive index of your that particular signal because of variation in the phase, or we can say that a variation in the intensity pattern, and then that will produces a signal that is about, we can say that it will produces a variation in the refractive index, or we can say that according to the variation in the intensity, it will produces a pattern of a refractive index distributions, and that will be proportional to the electric field here. Now this is just like, we can say that according to the variation in the electric field, we'll get that a variation in the refractive index profile. Now in this particular case, two optical signals are used to obtain the refractive index profile of a optical fiber. That two signals are nothing but what? A original signal and a delayed signal, and that will provide you the what will be the variation in the refractive index. So another method is what? A near scan method. In the near scan method, if you see that we have the source, and that whatever the light coming from the source, that will be concentrated at the end of input end of optical fiber, this one, through the lens. This one is about a lens, this one is a source. Light is coming from this source, that will be passed through the lens, and then lens will concentrate your light at the input end of your optical fiber. Then light is propagating through the fiber, and then we have again another lens here. Light is coming from the fiber, then lens is used, and that lens is used to magnify the whatever the light from the light coming from the a fiber, and that will be traverse on this a detector there. So that's why a traversable detector. So here we can consider that a area of a whatever the area of a detector is there is a magnified. So that's why we will use a magnifying glass to propagate your signal, or to follow the signal on the a detector there. So generally we can say that it has a small active area of a photodetector, but here a photodetector will scan that field, and then again that whatever the scanning is takes place, that is about a traversable scanning is takes place, so that it will receive the a signal, and then we will use a preamplifier for amplifying the signal, and then we can use that lock-in amplifier, and here we have used a chopper. That role of the chopper, that is, it will sense, that chopper is a phase sensitive here, and it will plot that whatever the signal amplified on this XY recorder, and so we will get directly a what will be the refractive index profile of your optical fiber. This is a near field scanning. Another one is about a refracted near field scanning. In a refracted near field scanning, here a source is there. We can say that there is a light, and then light is focused inside the particular fiber. So whichever the light is propagating through the core of a fiber, and whichever the light is propagating through the cladding of the fiber, that power is to be measured here, because a power is nothing but what? It is a function of whatever the light is propagating through the a particular fiber. In general case, if you see that the light is incident inside the fiber, so according to the numerical aperture of a given particular fiber, so it will propagating through the fiber. Means for a given particular fiber, there is a maximum acceptable angle, and above that your signal will be refracted. So now that's one. This is about a part of a refracting a signal out of the fiber that is in the cladding layer or out of that core here. And those who are within within that acceptable angle, that will be propagating through the fiber. Means we'll get a two power. One is propagating through the fiber and another is out of the fiber. Now you can see that this one is about a ray trajectory here. So in which you can see that your signal rays are propagating here through the fiber core. But because of that incidence angle, that is about, we can say, theta 1, is not belongs to the acceptance angle of the fiber. So that's why that signal will be refracted inside the cladding here. So that's called as a theta dash here. So theta dash is the incident angle. Here we can say that a actual, we can say that the angle of your signal there inside the fiber, that is theta, and that theta dash is about the refracted signal angle here. Now here we will measure that what will be the signal refracted outside the fiber core, and that power is to be measured. So that is about to output what will be the signal in that particular theta dash that will be detected, and then we will measure the power and what will be the power propagating inside the fiber core, that is about a PR here. So detected optical power is generally where you can say that it is a function of radial position of the input beam P of R and P of A corresponding to the input beam being focused into the cladding. Means that is about a cladding here. So we can find out the refractive index profile N of R is equal to what? What would be the refractive index of a cladding here with respect to what will be the power detected here. Now in this case, if you see that a theta dash, it is the angle of incidence in the fiber core, and then theta is the angle of a refraction in the fiber core, and theta dash is the angle of a refracted ray external to the fiber core, that is in a cladding layer. So we will observe here what will be the a minimum corresponding angle of the incidence, that is about a theta minimum. Generally we can say that a light at an angle that is theta dash greater than theta dash minimum must be allowed to reach to the detector. Okay, so what we can say that the light at an angle of incidence theta dash, it is greater than that a theta dash minimum. That light will be reached to the detector here. So that is about a process to ensure that light is to be reached to the detector to measure the what will be the a refractive index of the a refractive index profile of the fiber here. So now here we can see that another method of a measurement, that is a fiber cut wavelength measurement. Now that fiber cut wavelength measurement, because generally we say that if we consider the fiber, so the operation of a fiber, whether it is a single mode or a multi mode, it is depending upon that a cutoff wavelength of a fiber there. In general, if you see that if it is a multi mode fiber, so it has a many cutoff wavelength because that multi mode fibers has a number of modes propagating, and that number of modes propagating, they have the a different wavelength there. So that's why for the given particular fiber, what will be the a cutoff wavelength, so that is to be measured here. So to consider that a cutoff wavelength measurement, we need to consider the multi-mode fiber. We'll consider here a graded index fiber which has a parabolic index of a parabolic refractive index profile. Now you can see that, and for this particular fiber, the number of guided modes is equal to what? Pi a by lambda raised to alpha, that is 2, and n1 square minus n2 square. Now in this case, we consider that a light is propagating through the fiber, means light is launched inside the fiber here. This one is about the length of the fiber. Here is one turn, that is called a single turn fiber, and we'll receive that. Another case is about here. Here is the light is launched inside the fiber. Here instead of a single turn, so that is about that fiber is about, here is a radius here. It is about a case, we can say that a split mandrel case here, and then your fiber will be received. That length of the fiber in the two cases is same, but here it is taking a single turn, so it has a two turn. Okay, so likewise we say that this is about, instead of we are saying that a single turn, so that is about a technique here, a split mandrel technique, and the same length of the fiber is. Now using that single turn of a fiber, because of a single turn, fiber will be bent, and because of that bending, there will be attenuation, and that bending attenuation is calculated using 10 log of what will be the PS of lambda. PS of lambda is nothing but what? What will be the input power through this particular fiber? And here we can say that a PB of lambda, that is a transmitted spectral power, and this is about a power transmitted through the A fiber here. So generally we say that if for a given particular fiber, so effective cutoff wavelength, if we consider that a single wavelength, or we can say that a step index fiber, so it has a single wavelength, and in that case generally we say that a LP11 mode is propagating through the fiber. But in the case of a attenuation to be considered, so we need to see that a LP11 mode is to be propagating through the fiber, and that LP11 mode, it is depending upon that a length of the fiber and its radius of a curvature and the effective cutoff wavelength, then it will be vary based on the fiber optic fiber length as well as the what will be the curvature. Now this technique is used here to measure the what will be the fiber cutoff wavelength. So we will, first of all we calculate that what will be the band attenuation, and that is depending upon that what will be the difference in the total power transmitted and the fundamental power transmitted. So fundamental transmitted power, generally we can say that that is about a smaller transmitted spectral power that will be transmitted when we have the LP11 mode, that is called as a PB of lambda. That is a transmitted spectral power when we have the fiber is operating at the LP11 mode. And a PS of a lambda, that is about a transmitted power through the fiber, in which we consider that a given length of the fiber is to be considered, and a total input power launched inside the fiber in the higher order modes. Okay, so now this one is about a transmitted power at higher order mode, and this is about a transmitted power at a LP1 mode. That's why we will calculate that what will be the attenuation there. In general, we can say that a band attenuation here, it is depending upon that what will be the mode, because mode is depending upon the a wavelength there. So that's why that band attenuation, that will be depending upon that a wavelength here. So if we consider that a small loop of a fiber, or we can say that a fundamental mode of a fiber, so according to that, a band attenuation will be different here. So here the band attenuation against the wavelength in the bending method for the measurement of the cutoff wavelength. Now this graph is indicating that here this one is about a cutoff wavelength and this one is about the curve for the bend attenuation here. And if you see that here there is a difference of a level that is about a zero point 0.1 dB at which that a bend is occur because of that a mode LP01 mode, so that we will calculate that effective cutoff wavelength here. Now next is about the another method. We can say that we will calculate that a relative attenuation between the power launch into the a multimode fiber and a single mode fiber, and we will calculate that what will be the relative attenuation here. So this is about a PS of lambda, that is nothing but a power launch inside the single mode fiber, and PM of lambda is nothing but the power launch inside the multimode fiber. So generally we say that power level difference is depending upon that, or it is a function of a wavelength. So that's why that relative attenuation is again the function of wavelength. So that's why a relative attenuation versus a function of a wavelength. So that's why we can calculate that what will be the attenuation with respect to the wavelength here, and using that we will get that a attenuation. So in that particular curve, we will consider that a zero point 0.1 dB here. Okay, that particular difference. This line and parallel line to this zero point 0.1 dB at this particular point will get that a cut wavelength here. Means we will calculate that this one is about a straight line of this particular curve, and we'll get that a zero point 0.1 dB less here. So that is about this particular point, and we'll get that a of a cut cutoff wavelength for this given particular fiber there using this relative attenuation measure. So another measurement is done using a spot size. So in this particular spot size, the fiber is operating in the given particular mode. Generally, we will consider that a fiber operating in a single mode to get that a particular spot size, and that a spot size is increases linearly with the increasing the wavelength. You can see that, and here we will observe that a cutoff wavelength at this particular spot where we have this particular line, another line crosses at that particular point, and we'll measure the a cutoff wavelength. We'll get that one slope is positive slope and negative slope, and at this crossing of this particular slope, we'll measure the what will be the cutoff wavelength of the fiber there using the spot size technique. Next one is a fiber diameter measurement. In a fiber diameter measurement, we will use that a fiber. So what will be the outer diameter of a fiber, and that outer diameter of a fiber is to be obtained using the light propagating, inserting that fiber inserted in between that light and a detector there. Now here the combination of a mirror and a fiber is used here. Source we have, generally we can say that a light source is considered here. We will consider that a G1 and G2, these are nothing but a two lenses, and that two lenses are used to propagate a given particular operating wavelength of a fiber there. That's why that two different lengths. Then there are the two mirrors. That output of that two mirror, one mirror is given to the galvanometer here. That is, and that M2, because of that a mirror here galvanometer, so it will rotate through a small angle at a constant angular velocity before returning to its original position. This is about a mirror here M2 here, and then these are the lens C3 is used to focus the light on the fiber. This one is about a fiber here, or you can say that light is focused on the particular fiber. And then after that, we have the photo detector there. So the light is incident on this photo detector because a laser beam is focused on this particular fiber, and then we have the a fiber is act as obstacle here, and we will measure that the light on this particular detector there. Means we can say that that light will be blocked by the fiber, and other than block light that will be detected by this photo detector there. And because of that, we will calculate that what will be the a fiber diameter there. So here we will use that a mirror M2. That mirror M2 is a oscillating mirror. That oscillating mirror is oscillate according to the what will be the sweep we are using here. According to that, that mirror is oscillating here. And because of that oscillating mirror, that light is fall on this a fiber. It has a velocity, and that velocity is depending upon that what will be the blockage there by the fiber with respect to time. And that's why that at the particular photo detector, a light is reached with a velocity of a mirror there, that is by the d phi by dt. And according to that, we will measure that a diameter. So this is about a ds by dt. It is nothing but the velocity of the fiber shadow, ds by dt, and d phi by dt is nothing but the mirror velocity. Okay, this is about a mirror velocity, and will that L is the distance of the a fiber. And then we will calculate that a diameter of a fiber, that d is equal to what? It is depending upon that what will be the pulse width W here at the detector, and that is related to the what will be the shadow of a fiber, velocity of a shadow of a fiber here, ds by dt. So we'll get the directly d0, that is nothing but the fiber outer diameter. Directly we'll get the fiber outer diameter. So then another method is about, we can say that a core diameter. Generally, if we consider that a core diameter of a fiber, it is depending upon that what will be the core size of a fiber. So if we consider that a step index fiber, what will be the variation in that particular step change occur inside the particular fiber, we can find out the what will be the refractive index profile at the core and cladding interface here, if we have the step index fiber. But if it is a gradient index fiber, then in that gradient index fiber, so to obtain the core diameter of fiber, it is difficult because that refractive index of that fiber is varying through the core. So that's why we should know that a refractive index profile of the fiber to obtain the core diameter of a fiber here. So already we have seen that a method for the refractive index profile. So according to that, through that particular method, we can measure the what will be the core refractive index of the fiber, core diameter of the fiber there. that is about your a portion of your a fiber index or a core diameter measurement or a measurement topic of optical fiber here. And we have seen that a measurement of a attenuation there, and inside the measurement of attenuations we have seen that inside the particular fiber, if you see that, we have seen that a cutback technique, and we will measure the we have measured the what will be the attenuation there. And again we have used a calorimetric measurement for the fiber absorption losses, in which we have measured the what will be the heat generated because of that light is absorbed inside the fiber, and that heat generated, that will be measured using the calorimetric method. Then we have measured that a fiber dispersion measurement and a fiber scattering losses measurement we have seen. In this fiber scattering loss, that light is scattered outside the fiber core, and that light is scattered by the fiber core, that will be measured using the is solar cell cube of a that detector there. And whichever the light is scattered from this particular fiber core, that will be detected by this a solar cell, and in which that six solar cells are used to measure the whatever the scattered light propagating through the fiber there. Then we have seen that a fiber dispersion measurement. In the fiber dispersion measurement, we have used a two technique for the measurement of a fiber dispersion. One is about a time domain measurement, and another is about a frequency domain measurement. So in the time domain measurement, we have measured the what will be the pulse width or arrival of a pulse width that we have measured, and according to that we will measure the a dispersion there. And in this case we say that a optical bandwidth of a fiber is depending upon that what will be the dispersion inside the particular dispersion due to the fiber. Then in the frequency domain measurement, we have considered that a spectrum analyzer, and we have measured the spectrum of a receiving signal, and according to that we will calculate that what will be the a dispersion occur inside the fiber. And here for the dispersion we have obtained that what will be the a group delay, and that group delay is depending upon that a length of the fiber, and then a phase angle and the operating frequency. And then we have seen that a refractive index profile measurement, in which we have seen that interference microscope is used for measuring the refractive index profile of the fiber. So that is about the measurement of a optical fiber. And in next lecture we will see that what will be the a wavelength division multiplexing and why it is